like to spend a little bit more time investigating, however, some of the little quirky behavior in terms of the actual numbers. You might have noticed when you look at the graph above that going from beryllium to boron, the ionization energy in fact decreases. Or going from nitrogen to oxygen, the ionization energy in fact decreases as well. Now, if it only happened across one period, you might say it's kind of an anomaly. But you may have also noticed that going from magnesium to aluminum, the ionization energy decreases as well. And of course, magnesium is right below beryllium, and aluminum is right below boron. The ionization energy decreases in going from phosphorus to sulfur. Phosphorus is right below nitrogen, and sulfur is right below oxygen. There's something going on here. And so I'd like you to be able to explain why we have these dips in ionization energy. And it's also interesting that these sorts of dips happen because they give in a sense a view of the electronic structure in the atoms, and in fact support what the quantum model is predicting. So now let's take a closer look. So in teaching model number 3, we see the ionization energies for the second period going from lithium to neon. In going from lithium to beryllium, we see that there is a general increase in ionization energy, as you would expect if the nuclear charge is increasing. And of course, that's overriding the electronic repulsion. I then have a dashed line, which in a sense shows how the ionization energy would increase if all that was happening was that the nuclear charge kept on increasing and overriding the electronic repulsion. And in a sense, if all the electrons that were being removed from the same subshell, let's say all from the s orbitals, then that's what would happen. Of course, that's not quite possible because we don't have enough room in the s orbital. In going from beryllium to boron, you see that the electron will be removed from a p orbital, as is true from carbon, as is true from nitrogen. And so I have solid arrows pointing downwards from the dashed line, indicating that the ionization energies are less than what you would expect because the electrons are being removed from a p orbital rather than an s orbital. When I say less than what you'd expect if all the electrons were being removed from the same orbitals. In going from nitrogen to oxygen, in fluorine and neon, you'll see in a sense that all of those ionization energies are yet further reduced. And this has to do with the fact that the electrons are being removed from spin-paired orbitals. Okay, now that's an overview. I'd like to get down, in a sense, to a little more nitty-gritty in the actual explanation. So moving to the next key question and this chart here, we're asked to explain why there's a dip in ionization energy between beryllium and boron. Now we're going to be able to explain this. If you are, for instance, you're asked in an assignment or a quiz or a test, you would be able to produce an orbital diagram something like what I'm showing you here. So we've got the beryllium, the boron. I've written their nuclear charge. I've written the orbital diagrams. I'm also trying to indicate that the 2s orbital is of higher energy than the 1s. And more importantly, the 2p orbitals are of higher energy than the 2s orbitals. Okay, so starting from beryllium, the first ionization energy would involve removing an electron from an s orbital. That is one of the electrons in the 2s orbital. Going to boron, you can see that the first ionization energy would involve removing the electron from a p orbital, the 2p orbital. Now I've arbitrarily stuck that electron in the 2px, but of course it could be in the 2py or the 2pz. Now going from beryllium to boron, the nuclear charge does increase. So normally we would expect an increase in nuclear charge and that the ionization energy would be greater. And when you're developing an explanation, I think that you should state that so that we would say something like, although there's an increase in nuclear charge from beryllium to boron, and that sets up that we acknowledge that there is an increase in nuclear charge. But there's something else to consider. The valence electron will be removed in the case of boron from a higher energy p orbital, and that makes all the difference. If the electron were to be removed in boron was actually from an s orbital, this would not be of a higher energy. So in this case, the valence electron to be removed is in a higher p orbital. Therefore, a smaller ionization energy is required to remove that electron. And so this explains the dip. There isn't a dip in going from boron to carbon because they are both having the same situation. Both of them are removing an electron from a higher energy p orbital. So the effect of an increase in nuclear charge is in fact experienced and demonstrated. So this is the kind of answer that I would be looking for to explain the dip in ionization energy between beryllium and boron. The same explanation would be applied to why there's a dip from magnesium to aluminum, or why there's a dip from calcium to gallium. Hopefully this discussion makes sense to you, and we'll be looking at some similar examples in our live sessions. In the key question number 3, you're asked to explain why there's a dip in ionization energy between nitrogen and oxygen. So once again, we notice that the nuclear charge is increasing and going from nitrogen to oxygen. So we'll make that statement. Although there's an increase in nuclear charge, looking at the orbital diagrams, and make sure you know how to write these out, if we think about, well, which electron will be removed? Which will be that first electron corresponding to the first ionization energy? In the case of nitrogen, it could be any one of the electrons in the 2p orbitals, because they're all the same energy. They are degenerate. Whereas in the case of the oxygen, we know that the first ionization energy will be the energy required to remove the electron that, in terms of how I've drawn it here, is in the 2px, and it'll be removed from that orbital because it contains spin-paired electrons. When the electrons are in the same orbitals, they have opposite spins, but they still experience greater repulsion than the electrons that are in different orbitals. And so yes, the nuclear charge does go up, but because of this greater repulsion, it's easier to remove that electron. And so we can make a statement something like, the valence electron to be removed experiences a greater electron-electron repulsion, and therefore a smaller ionization energy is required. And so it is important to acknowledge that there's an increase in nuclear charge from nitrogen to oxygen, but then state that the valence electron to be removed in oxygen experiences a greater electron-electron repulsion, and therefore a smaller ionization energy is required. You can see that the two explanations are similar, but there's an important difference for why there's a dip between beryllium and boron and a dip between nitrogen and oxygen. And of course, this last explanation would also apply for dips from phosphorus to sulfur and arsenic to selenium. So make sure that you can make these sorts of explanations. We've looked at the trends related to the atomic radius and the trends related to ionization energy. The last trend is related to electronegativity.